Thank you for the not entirely truthful introduction. Thanks for the organizers for inviting me and organizing this wonderful workshop that so far has been really interesting. And I apologize if my voice doesn't break very well. I'll try to do my best. Indeed, so my original topic was something about gallstones. I was very happy to talk to anybody who's interested about that, but in preparing the talk, I sort of ran out of time, so I said to talk about something that was a bit easier to present systematically. It's based on work that I published with Sagar last year in April, and also a couple of years ago with Finn, who's a student in Durham. And it's about something we call symmetry descent, which builds very naturally on the kind of things that Federico was talking about. So the context here is that we are thinking about the string theory as a tool for associating quantum field theories to singular manifolds. We call this geometric engineering. So here we are not thinking about string theory necessarily as something that will teach us about quantum gravity. It's of course a wonderful tool for that, but here is a tool for learning about quantum field theory. And in this way we think of the geometry X that defines a theory, and we want to extract the symmetries of the theory. We want to extract this thing we call the SymTFT for T of X. And this is a topic that has a lot of history by now. Many papers have developed this point of view of the SymTFT. And the thing that sort of motivates this approach is that typically it's much easier to understand the SymTFT than the theory itself. So the dictionary from geometry to quantum field theory can be quite involved. The dictionary from geometry to symmetries tends to be much easier to understand. So I want to derive some results in the two papers that I just mentioned that give you we are working towards a systematic approach of doing this. And basically we like to have a machine, a well-defined mathematical framework that just gives me geometry and will give you some topological field theory, which is the SymTFT that Federico introduced. And this is in principle the thing that you don't need to do if you know enough about the Lagrangian of the theory, but if you come, as I do, from the context of geometric engineering, we almost never have Lagrangians. That's a luxury that almost never we can enjoy. So if you don't have a Lagrangian, what do you do? Well, typically the thing you want to do at the theory when you don't have a Lagrangian is you want to understand symmetries and anomalies and that kind of thing. So we have to, because we have nothing else, to derive that from the topology and metric of the space X. And this is when things are most valuable, when you don't know the Lagrangian, at least you know the symmetries. Hopefully you can say something useful from there. And so this talk could branch in many ways because we know there are many formulations of string theory. In every formulation there's typically more than one way of constructing field theories. Luckily, the ideas translate very well, so we have many dualities that allow us to go from one language to another. So in this talk, mostly I will work in M theory, which is an 11-dimensional version of string theory, type 2B, which is a 10-dimensional version of string theory. The details are not going to be important, so you're not a string theorist, so if you don't care about the string theory, it's totally fine. I will tell you everything that you need to know about these theories. And again, there's many ways you can go about, even once you fix the theory. I'm going to sort of work in the simplest case that, again, easy to translate to other formulations. I tend to like to work in the one that's purely geometric. So you have some cone, that's X, that has a base, B, and it has a singularity. And because there's a singularity, if you follow the rules of string theory, you will learn that there's some interesting local degrees of freedom in the singularity. They come from branes that become light. So basically in the singularity you can think of some cycles, some subspaces becoming small, and the objects that wrap these cycles become light, they start interacting and things become very interesting. So we have a lot of very interesting stuff here, and away from that we have basically understood or understandable supergravity. And sorry, the way I tend to draw these drawings, I have internal space X, and then I have a space M, which is tensored with this Cartesian product with this space. And M is where the field theory lives. So more precisely, the total space is localized at this point times M. Okay, so it's an M-dimensional theory that comes from the modes from branes or whatever it is at this point here. And you can do many things. So, for example, Federico was explaining a case in which was not exactly of this type. It was not exact cone. But just for simplicity, I will study cases that are cones. Another thing that we'll study is the case in which X is non-compact. And that's because I want to talk about symmetries. And we have learned during the workshop or in a few talks that seems to be the only meaningful thing you can say about symmetries in gravity is when you have non-compactness, when you go to infinity, and then you can say something like how symmetries act on your boundary conditions. I'm going to work in geometric engineering. It's a little bit more general than, well, it's different, I should say, than the things you can say in holography, but the ideas translate with minimal changes. So many of the things I say have an easy translation to holography. And as I said, just to make our life simpler, I will assume that X is a real cone, so it's a proper cone. Federico already mentioned a case in which it's not a proper cone. It had a deformation at the bottom. The ideas still work the same because we care about the infinity, really. I'm going to assume the field theory is supersymmetric. So we have the Calabi-Yau. This is the technical condition. And the origin of all this structure that we're going to discuss is the fact that whenever you have a string theory or any field theory, really, on a non-compact space, you have to tell me what happens at infinity. We don't do a path integral where the field's at infinity. We fix boundary conditions, and you have to tell me how you have fixed those boundary conditions. So the space where you fix these boundary conditions, assuming that X is a cone with base B, is the form, the base of the cone. So this is a cone with base B, and infinity looks like B times this manifold M. Okay, so you have to tell me something that happened in this manifold B times M. So this is the supergravity question. How do you fix the supergravity fields, so string theory fields, in this non-compact space? The translation to field theory is that once you have fixed the supergravity fields, you are giving me backgrounds for your symmetries in the path integral of the field theory. So as usual, whenever you have a path integral in field theory, it depends on the background fields for the symmetries, and those get mapped to the supergravity fields. Okay, so in practice, how do you do? Well, you would have to give me a state in the Hilbert space associated to quantizing gravity in here. That's a terribly difficult problem, which probably doesn't make a lot of sense. But for connecting to field theory, all we need to say is in which topological sectors the fluxes live. And typically, you would imagine that you just put the fluxes to zero, which we always are told to do in compactifications or whatever. There's a canonical vacuum, but a very crucial effect for us, shown by Greg and Dan, Greg and Graham Segal, is that in the string theory, the fluxes that you want to fix at infinity don't commute with each other whenever B has torsion. And that has the property that there's no canonical choice for the fluxes. There are some choices that you have to make, and these choices are the origin of this whole story. So this is a very well-known stuff. In paper from many years ago by now, we argue that some of the things that you see in field theory, the reading between the lines, for example, can be reproduced by looking at these fluxes. I'm not really going to talk about that too much. It's at the bottom of everything I'm going to say, but that's, I think, by now fairly established. I'm going to here think out a picture that's sort of equivalent to that, but not manifestly, which is the SymTFT picture. So if you think about what we had in the previous construction, I think I have a picture somewhere. Here, so we have a field theory that lives sort of here, and in the language of field theory, you could say something like it's relative to a 10-dimensional, 11-dimensional background. To really give meaning to this theory, you have to tell me what happens in the higher dimensional geometry. Now, in the recent literature in field theory, we have learned our relative theories, but typically we like to think of them as relative to one dimension higher. And the theory that are relative to in one dimension higher, the SymTFTs, the theory that Federico already reviewed very well, that explains how the symmetries of the theory arise. Right? The topological operators here that survive the sandwich. So the challenge in front of us is connecting the picture of geometric engineering or holography to the SymTFT. So here's the basic way in which you can do it for geometric engineering. In a paper with Federico and other collaborators, we worked out that what you need to do is you start with the geometric engineering background, X, and when we're thinking about it, you do a deformation of this because you're after a topological phenomenon. This is not going to really change much, so just the way of thinking if you want. I'm not really doing anything here. And if you now think of taking the supergravity here and somehow compactifying on B5, this will give you a topological field theory, the SymTFT. Now, this was understandably a little bit blurry, so I was waving my hands. And the rest of the talk, the goal will be to give you a precise way of computing this. Right? But intuitively, what I'm doing is what you should also imagine that you're doing holography, which is take the internal space, in this case the base of the cone, and do some sort of reduction of the topological operators in there. Whatever that means. I want a way of doing this systematically. Okay. So just to connect a little bit to see what we should expect. In supergravity or string theory, I need to fix the boundary conditions at infinity. In the SymTFT picture, that translates to fixing the gapped boundary. I also have the gapless modes here in the sandwich. Those correspond to the degrees of freedom that live here, and the SymTFT is in the middle, interpolating between them. Okay. So in that previous paper with Federico and company a few years ago, we worked out some examples in which the SymTFT looked like this. You had some BF sector, some discrete gauge theory sector, and then some anomaly sector, if you like. And one thing that we had to do in that paper, because at the time that's all we knew how to do, is we had to use different techniques for deriving the BF term and the anomaly term. So the BF term we argued just by looking at topological operators of the theory and seeing that they didn't commute as they didn't commute in this paper, so we could reproduce structure of BF theory. While for the anomaly term, the way we argued was by looking at the action of M theory. In particular, we had to consider these famous terms. I'm omitting a 1/6 and some subtleties here, but there's this famous Chen-Salmons coupling M theory. We took that, we put in a space with torsion, did hard computation, got coefficients, and those are the anomaly coefficients. So that was great because we could compute the coefficients, but also made me very unhappy because we had to do two things to derive one object, right? That's not a very happy situation. So in this paper with Sagar, we suggested a procedure that gives you the whole thing at once. And basically, as I warned you, it's possible this talk finishes in the next 5 minutes because my voice is almost gone. I've been told there's no microphone, so I'm doing my best. So we wanted to do the whole thing at once. And there's basically two options. You can compute the anomaly by looking at the topological operators in string theory, see how they don't commute and so on. So generalize this to the anomaly, or you can do the dimensional reduction also for the BF term. Two things you can do. We went with trying to understand the BF term from a dimensional reduction. There's some really nice papers from Michele and collaborators, and Kaidi, Nardoni, Safri, and Tseng, where they go the other way, so they can understand the anomaly terms from the brain dynamics. Okay, so these are complementary, and I expect they are all compatible, as far as I know they are, but it will be really nice to sort of merge them together. Anyway, we're going to try to do dimensional reduction. Let's try to understand why that's hard. And the basic problem is the following. In the B wedge DC sector, you think out the origin of B wedge DC, and the thing that gives you the discrete gauge theory, the finite gauge theory. B comes, if you like, from the C3 field in M theory, so the electric field in M theory, and C comes from the magnetic field, C6. Okay. So you're trying to somehow start with an action in 11 dimensions, dimension reduce, and write an action that depends on the electric and magnetic field. So the obvious thing you'll want to do is construct an action that works democratically. Both C3 and C6 appear, and then you reduce, and then you get what you want. And of course, this is a problem that is studied since forever. And there are many proposed solutions. Here are some of the main papers I know. There are probably many others. I'm going to describe in a second how we are going to approach, but it's basically following the approach in Bellow van Moor and Sieta Chikao and Yonekura, with small variations. Okay. There's other things you could do, and basically any paper in this list gives you a way of attacking this problem, but to us this was sort of the cleanest that we knew. And as I will explain later, it's very nice also in that I will be able to say something on continuous symmetries too. So that was the topic of the paper with Finn a couple of months ago. So, some very wise. So, can I go and get some water? Okay, thank you. So, let's try to understand what happens, how this happens. So remember that what we're after is putting M theory, or whatever supergravity we have, in B, and B, importantly, is a space with torsion. That will be the key point here, okay? So let's try to do an example, which is generalized Maxwell, and by that I mean the theory with p-form connection AP, which has an action of this type, so Fp plus 1 is just the AP. It's a Maxwell, but just with a p-form. And this is the theory that, as we all know, has U1 cross U1 symmetries. All right. This is sort of the electric presentation. Of course, there's a magnetic presentation in terms of a dual field, which is a D minus P minus 2 connection. And in order to see this B and C, we need the formulation that sees both things at the same time. So how do you do that? So I'm going to, as I said, go with this point of view in which we think of our theory, in this case generalized Maxwell, but I want to think of string theory also in this language, as an edge mode of a theory in one dimension high. So the right theory for understanding Maxwell, for example, this generalized Maxwell, well, the right theory, one good theory for understanding this is Maxwell BF. So what's Maxwell BF? It's a theory which is a BF theory, of the type we want to understand. These are level K, with a B and a C, which are U1 connections of these degrees. And then you give kinetic terms of B and C. All right. Maybe one thing I should say, some of you I'm sure know this, but for those that don't, you should think of B as taking the field strength in this generalized Maxwell and making it a dynamical connection in the bulk. You can notice the degrees here. The degree of B is P plus 1, having an AP connection on the boundary. So what's happening is that the F, if you want, on the boundary becomes a connection on the bulk. That's one way of thinking of this. A bit very heuristic, but that's one way. And C, then you can think of as the field strength of the dual connection. Okay, so away from the boundary, here somewhere in the bulk, these fields have a mass which is proportional to a level, but then the E square and M square, EM and M are the things that tell you about the kinetic term here. So when you introduce this kinetic term, this will give you a large mass. So a small kinetic term is a large mass for these guys. It's a very small deformation of the BF theory. So in the limit in which this is very large, or if you want a large distances, you recover the BF theory. All right. So what happens on low energies is that you end up with flat connections, right? Because that's what the BF theory does. The equations of motion of the BF theory, if you forget all this term, will tell you that dB is 0 and dC is 0. As well. Okay, but there's something interesting. So here I'm happy to be corrected. This paper by Sieta Chikao and Yonekura is the first paper I know where it's said, although I'm sure other people knew this before, that there are classical solutions of Maxwell-Chern-Simons theory that localize exponentially close to the boundary. So that's a very interesting result. And the same thing is true for Maxwell BF. I'm going to explain this in a second, how this works. But the picture is that away from the boundary you have yes, BF theory, topological, all that. And you have exponentially localized modes. But the really nice thing in this paper is that they show that this thing is a purely classical analysis. See?
Do you get standard Maxwell theory for any value of k, or just for k plus 1?
Just standard. Yeah, it's Maxwell theory. Yes, standard Maxwell
For
theory.
any value of k?
Yeah.
Because it seems like it would be a relative theory if k is bigger than 1, because then you have a topological theory.
Yeah, but that's more about the gapped boundary.
Uh-huh.
The thing you can do the gap boundary is of the gapless boundary.
I see.
So effectively you're going to be rescaling the periods.
Yeah.
So of course you can, yeah, if you put k different from 1, you can play with that, but for local dynamics it's not going to tell you anything interesting. Thank you. I should say, please interrupt at any point. Okay, so what the Garcia-Etxebarria and Iñaki were after in this paper was a way of understanding the self-dual field, which is of course famously difficult. But for us, that we just want to understand Maxwell, all we need to do is take the result of Maxwell Chern-Simons and translate it to Maxwell BF. Just, go through the same calculations, they're not very hard, so let me summarize them, and you find Maxwell BF. So basically you look at as an ansatz for the solutions, which is localized exponentially close to the boundary. And if you now try to ask that this ansatz satisfy the equations of motion, what you'll have to impose, it's a very short exercise, is that f and g need to be flat. And they need to be dual to each other, dual in this sense. A star of f, where the star is the boundary star, is equal to g. Okay, these are the equations of motion of Maxwell BF for this ansatz. F here is something that depends on the boundary only. So I have a transverse direction that goes exponentially and f and g. Okay, so again, you can sit down and do this in a minute, and it tells you that you have an f that moves as Maxwell's field does. Okay, so let's choose boundary conditions for actually getting this exponential mode. And the boundary conditions that you can choose, one set of boundary conditions that you can choose, which are useful, are b equal to c equal to 0 at the boundary, which for me is at t equal to tau equal to 0. Okay. All right, so this is not the only boundary condition that you can put. You can put any constant here, the usual thing, right? You can turn on backgrounds and so on, but for the point I want to make, 0 is good enough. And interestingly, putting this boundary condition does not kill the ansatz that I just explained, because in the bulk, all you need is that B and C become flat. And flat, if you don't worry too much about topology at this stage, means that it's pure gauge. So as you go to the bulk, a set of solutions that goes to 0 at the boundary and becomes pure gauge on the bulk looks like this, where F and G are pure gauge. Okay. So pure gauge means that they are D of some connection in 1 degree higher, a degree lower, sorry, like here. Okay, so this is a solution of the equations of motion, the family of solutions of the equations of motion. But it gives you an interesting perspective on the Maxwell fields on the boundary. So you can think of the Maxwell fields in Maxwell theory as gauge parameters of BF theory in 1 dimension higher. We have put a boundary condition which is not gauge invariant. All right. So this is, I think, a nice way of thinking of things. This is the sort of Garcia-Etxebarria and Iñaki. Let me comment briefly on an approach which is understood from much before, and which ends up being equivalent, but somehow easier to work with. And this is something that many of you know. I just want to explain the connection. So let's think about what happens in the limit in which E and M goes to infinity, right? So I like to divide the geometry into these 3 regions. There's a region here, some characteristic scale that depends on M and E, where you see these Maxwell modes. They localize more and more as you tune E and M. You have a region which is near boundary, where you don't see the exponential modes, but still the geometry is essentially a cylinder. Right? As I make E and M small enough, I can always make the cylinder in the scale limit large enough. And then I have the rest of the bulk. Okay, so this field, the Maxwell field, as I go to the bulk, becomes pure gauge, becomes just F and G, which were pure gauge. So for an observer that doesn't really see this bit and just sees the near boundary bit, all they will see is that a bunch of gauge transformations here the gauge parameters that determines these gauge transformations are controlled by the Maxwell equations. So an observer that's trying to model this system could just write a Lagrangian for the gauge parameters on the boundary, which is Maxwell's Lagrangian. Okay. So this was precisely the coupling that was introduced in Maldacena, Moore, and Seibert to understand the singleton mode in holography. From this point of view, it's a coupling that tells you that the gauge transformations of B are no longer gauge transformations, they change the action. And they are controlled, the dynamics of these gauge parameters, by Maxwell theory. So it's a different way of thinking about the same dynamics, but now from a point of view in which you have forgot about all this stuff about E and M, and your boundary condition becomes that B and C are pure gauge. Let them be oscillating, but they can oscillate only when weighted by this parameter, by this term in the action. Sorry. All right. So this second point of view is for me more useful. I'm mostly going to focus on this, but in my head, when it comes to any question about regularization and so on, it tends to be useful to go back to the E and M presentation. Okay. And now that we have this point of view about Maxwell theory, I want to now go back to the SymTFT and try to understand if I can obtain the SymTFT from dimensional reduction in this formulation that, as you see, treats the electric and magnetic degrees of freedom on equal footing. The bulk is BC, and B is electric, C is magnetic, and they're completely symmetric in the bulk, in the sense of this formulation doesn't care which one you choose to work with. Okay, and I should say there's other papers that take a somewhat similar approach, starting from the bulk. The details are different. Here I'm explaining our approach, which I like. So this is what we want to do. Again, we have this cone. We want to squish the base of the cone and get a topography theory. So let's see how this works in detail. Let's say that we have 4D Maxwell theory on a lens space. And if you do that, I claim, let's see how this goes, that in one dimension, in 0+1, you end up with a discrete CN quantum mechanics. So this theory is not completely trivial, even if S3 mod Seden has only the volume forms and harmonic form. So, okay, we have A, B, which are certain cochains in one dimension. These are the fields in the 1D theory. I want to obtain that effective theory. So here's the approach I want to follow. We are starting with Maxwell in some space where I want to obtain the effective theory times the compactification space, which I'm calling L. Think of lens space, something with torsion. Right? And I want to somehow integrate on L the topological sector, meaning I want to obtain this non-commutative structure coming from Moore and Segal. All right, and this is difficult because I don't have a good way of thinking about Maxwell in a duality invariant way. So what I'm going to do, I'm going to promote the Maxwell theory on X times L to a BF theory on Y times L, where Y is a manifold whose boundary is X. Okay? There's some issues what to do when X is not a boundary of something. We can discuss that. It's not very crucial for what I'm going to say. Now that you're here and you understand how to obtain Maxwell, right? You start with the BF theory here and you do gauge transformations. That's all you need to do. Now you can start with the BF theory here and integrate on L. Integrating topography theory is almost a nope, it's basically nothing. So that's easy typically. And then you get some topography theory and this manifold Y with boundary X. And now you do the gauge transformations here. This gives you an effective theory in X, which should be the same thing as you obtain here. As it turns out, these steps are much easier than that step. Okay, so let's do that. Here I have to go through some little technicalities. It's not going to be too painful. All I want to say is that we have a way of thinking about gauge connections in a way that we can understand topology. We keep track of topology. And for that, we use the Hopkins-Singer model. This is a model in which you represent the connection in a bundle by this triplet. You have some discrete data. This thing that you can think of as some sort of R extension of holonomies, like the people in the lattice sometimes do. I said to mention R value. You have done the lattice. So if you have done the lattice, if you does lattice, this is very much like the Villan formulation. You are familiar with that. So that's very close. And then there's something like the field strength, basically. Okay, so this looks like nothing particularly unfamiliar, perhaps. Field strength, connection, and this would be the characteristic class or some local version of that. But this is all the data that you need, and there's a nice structure on this. So you have a differential that equals to 0. You have a way of multiplying these things, which are differential cochains. And you have integrations. This is have a Stokes formula. So all the things that we like when doing calculations, they are still there. Okay. Just for concreteness, if you want to have a U1 bundle with a p-form connection, this is represented by a cochain of degree p plus 1, which is closed. The set means cycle here. So we have a closed p plus 1 cochain, a cocycle. And gauge transformations are d, so shifting a by d of something where the something has 0 field strength. Okay, those are the rules of the game. We don't need to know much more. Once you have this thing and the definition of the product, which is a little bit involved, that makes perfect sense. Once you start it for a couple of weeks, then that thing you can play with and do every calculation you want to do. So this, of course, might look like a technicality, but let me try to explain why this is important for the physics. And the reason for that is that in this way we are talking about the connection. Remember, the whole game here is do a gauge transformation and see how the theory changes. We don't want to work in a gauge non-invariant formalism. We want to work. So we don't want to work in a gauge invariant formalism. We want to work in a gauge non-invariant formalism. We want to see the A's and not the F's. So this is what this thing keeps track of, in a way that doesn't lose track of topology. And so this is the idea. We want to work with a non-gauge invariant field. These cochains are the non-gauge invariant fields. But if you want, we're always working at the level of Lagrangian densities and not actions. Okay. And why is this important? Remember that SymTFT is a gadget I want to put in a sandwich. And I want to obtain the SymTFT as an object on the boundary of something else. So I better work locally if I want to avoid having to work with corners. Okay? Working with corners will be a possibility. And during the last year, lots of people, including ourselves, have, with Jesus, have thought about corners, but it's painful. So if you want to avoid them, then you can just work in this local formalism, and you can still obtain everything you want. You still have to worry about the boundary conditions of SymTFT, but the SymTFT action itself you can derive. All right. So let's think now. We have the Maxwell theory. Remember, I'm trying to compute Maxwell on a Lens space. So I have the BF theory, one dimension higher. The BF theory is two of these connections with a star. This is how you represent in this formalism the BF theory. The details are not very important. And we impose the boundary conditions that these things are pure gauge, which I represent saying that the class of these things is 0. So if you now take this action here and you do a gauge transformation, which remember we're shifting by a dB and a d gamma, you can just compute what you get, and you get a boundary term, which is of that type. And you're interested in the case of flat backgrounds. Remember, this is some sort of reduction, so I'm going to restrict myself to a flat background. Typically, what you need to do when you do one of these things is a KK reduction, right? All the modes. So you might as well do that, but because we are working the limiting which this S3 is very small, all the KK tower is going to be not important for the topological theory within the IR. So I'm just going to keep the lowest level, which is the flat representative of the non-trivial cycles, non-trivial classes. So if I do the calculation here, I'm happy to explain details after the talk, but I don't think it will be fun for anybody to have to explain that during the talk. So this is the calculation that you want to do, and this is what you get. You get precisely what I promised before. These discrete cochains, which are these elements of the cycle with the ions in the right place, to give you the discrete quantum mechanics. Okay. So many of the details I am aware I skipped.
Sorry, what is the little h?
Yes, thank you.
That's the holography. Oh, that's the holography.
That's my, exactly, that's my notation for the
so you integrate it, you get a differential cochain, you take its holography.
That's right.
Okay.
Yeah, thank you.
Can I actually ask a question? So
yeah.
You've gone to a higher dimensional bulk to not have to pick an electromagnetic duality frame.
Yeah.
But if you're already working with differential cohomology, is there a reason why you don't want to just pick electric or magnetic, whichever you like, and just dimensionally reduce it on S3 mod Zn, you'll still get the Zn gauge theory. It won't have this action formula you want, but it'll be the same TQFT.
In this case, I suppose you can, thinking a little bit carefully. And for example, in the original paper by Greg and Dan, they derive a flux and commutativity working purely in the electric frame. That's entirely doable. But I'm going to later on work with the self-dual formulation of a string theory. So I want to eventually do this for K theory. And there it's very unnatural, I think, to pick a frame. You can definitely, so Bell Moore, for example, an example where that's developed carefully, but I find it easier to just work with the self-dual formulation, throw it to the calculator and see what comes out. Yeah. Any other questions? All right. All right, so yeah. So we started with the BF theory in product space, integrated and obtaining BF theory, and of course, the way to do that is going through the back. So, for those of you who have studied anomalies, this may be a little bit reminiscent of anomaly descent, in the sense that we find that the exterior derivative, in some sense, so remember that the SymTFT lives here, and it comes from taking the gauge transform and then going to the boundary. So we find that the gauge transform of the action in here is a exterior derivative of the SymTFT. If you have done anomalies, this is a bit like when you say the gauge transformation of the Chern-Simons gives you the exterior derivative of the anomaly. Okay? Same thing.
What's the capital delta sub lambda check?
Yeah, I'm sorry, just having the fine notation. This means gauge transformation. This is holography and this is exterior derivative.
So lambda is the gauge parameter.
Lambda is the gauge parameter. So this is a sort of symmetry theory promotion of the anomaly descent sort of formula. At least that's the way I like to think about it. Okay. So here comes the reason why I chose this formalism. Is because if you want to work with type 2 or type 1 properly, you want to work in K theory or twisted K theory. And in this formalism, at least formally, the modifications are fairly minimal. So there's a version of this differential cohomology for H twisted K theory. And just do the calculations there. Same formulas. To the extent that we can compute, we can reproduce many things. Maybe one thing I should say, once you generalize to H twisted K theory, you can now reproduce also the anomalies. So far I discussed the BF sector, but it's nice to reproduce also anomalies, and this formula packages everything, both the BF terms and the anomalies. So it's pretty neat. Let me in the last, 4 minutes of it? 5 minutes? Yeah. Okay, in the last couple of minutes, really, I'm going to discuss briefly the recent paper with Finn. And it's about continuous symmetries. So let me just sketch the calculation. The philosophy is exactly the same. Right? So we want to understand how continuous symmetries appear in the SymTFT. And you can do the same thing. We know since forever, from holography, for example, that at least certain continuous U1 symmetries come from having the internal space now with, instead of having torsion cycles, you have integers, free cycles, free cohomology, right? So the thing you want to do is, instead of reducing on a flat representative of the torsional class, you want to reduce in a harmonic form, like a standard KK reduction. Okay, so we just went through the exercise. It's really the same stuff, just with a slightly different expansion. So instead of expanding in torsions, you expand in free generators. You go through the computations, and what you find is this answer. So what do you get in here? You get some intersection number between the free generators in the internal space, as you might have expected. And here's the interesting bit, I think. When you put this in the Hopkins-Singer machinery, the thing that you get is a cut product of an N and a B. So the N is a bit like the characteristic class that we saw. Remember, Hopkins-Singer had a characteristic class, which was integer valued, a holonomy, and a curvature. So this is the characteristic class, and this is the holonomy. That's the kind of coupling that you're getting here. And this literally, again, is just putting the things in and doing the computation. So the characteristic class is an integer valued cochain of some degree, and this holonomy is a real valued cochain of some degree. Now, for those of you who have studied U1s, SymTFTs probably recognize this. let me point out. So you have this kind of BF theory. You can define operators, which are holonomies of n and holonomies of b. Now, one thing I should tell you, this is not immediate, but it comes again from the formalism, from keeping track of the gauge transformations, is that the gauge transformation of n goes by the exterior derivative of an integral cochain. So the gauge invariant operator I can construct is of this type, where alpha is valued in U1, and it's valued in U1 because n is integral. Okay, so that's the first operator I can construct. And the second one will be the holonomy of B. The gauge transformations of B are the sort of small gauge transformations, so this is a real cochain, and then the large gauge transformations where this is integer cochain. So if you compute the holonomies of C, now the coefficient here has to be integral because of the large gauge transformations, as usual. So we are getting in this representation of the theory, which is perhaps not the standard one, but it's the one that comes from Hopkins-Singer, naturally, these two sets of operators, which I'm sure many of you recognize, are the ones that are in these recent papers for the U1 theory. Okay, so it matches very nicely. One thing that sort of matches when you think about it, but not on the nose, really. One way of thinking about this structure is that this is what remains of Maxwell theory as you go to the infinite coupling limit, the limit in which you kill the kinetic term of Maxwell. But as I emphasized, we really want to work in a way that's electromagnetic duality invariant. So we should be able to access the E goes to infinity limit, E goes to zero limit, the opposite limit, so if you want the dual photon becoming topological. And we can do that. The way it appears in our formalism is exactly the way it appears in holography, in this paper by Witten and more recently generalized. So paper by Witten is about ADS4. Say that you have a three-dimensional CFT with a U1 symmetry. And he's asking, well, what happens when you take the U1 symmetry of this CFT on the boundary and you gauge it? How does the bulks react? And the idea is that the choice of boundary conditions that implement this gauging are related by SL2C. So the Wolf and Higg-Bottom generalized this recently to ADS of any degree. And this is how it appears in our formulation. You choose a duality frame, and depending which duality frame you choose, the actual couplings that you get are the different limits that you obtain here. Anyway, there's a small difference in terms of philosophy, but in terms of calculations, we get the same result as they do now from this procedure. Okay, so let me finish. And let me just list some open questions. So again, the hope here is to be able to build a machine that with sufficient computational power, you can just get a geometry and obtain a SymTFT. We are not there yet. There's things that I don't know how to do, at least in this approach. So M theory is a bit of a headache because remember that the bulk fields are like the field strengths, and M theory has a coupling which is something like G4 cubed. So I will need something like a BF theory where I have a connection cubed. I'm not quite sure what that is. Maybe somebody here can tell me, but I don't know what that is. This is something that Federico already said. So the SymTFT is really extended. There's a lot of data there. We want to reproduce all of that. So it'll be fun to try. And there's something Federico also said. Yeah. So maybe one thing I can say Federico didn't say is that there should be a generalization of this to non-abelian stacks, which I think is interesting. This philosophy of the edge modes being released by some small modification of the bulk is something I don't know how to do for non-abelian stacks. I think it would be really useful if we could do this. If we could view the non-abelian theories in the same way as the abelian ones. Okay. And with those open questions, I finish. Thank you.